Before I start, let me tell you what is the goal of this section. The goal in this section is that we want to learn how to integrate rational functions. So if I give you any rational function, how would you integrate that rational function? Okay? We have seen how to integrate rational functions in certain cases. That is, in some of the problems, remember, the derivative of the denominator was in the numerator, and we did a u substitution and things worked out. Right? But how likely is it that the derivative of the denominator is on the numerator? Well, not very likely. And so we want to learn how to integrate a rational function. Remember what a rational function is? It's the ratio of, what is a rational number? Ratio of integers. Rational functions, ratio of polynomials, right? So we want to integrate ratios of polynomials. And again, my warning is that if you think that you have seen the worst integrals in the previous section, remember the trig substitutions? Well, wait to see this one. Okay? So, all right. So here's let's say this function f of x that I have. This function that f of x that I have here, f of x, let's say, is a rational function. So that means it is the ratio of a numerator and a denominator. Both of them are polynomials, okay? And let's go back to our childhood and where you learn what is a proper fraction, what is an improper fraction, right? The number 3/2, is that a proper or improper fraction? Improper fraction. And proper would be 2/3. 2 divided by 2 would be improper as well. Now what's the difference? The difference is when the numerator is bigger, we call that improper. When the numerator is smaller, we call that proper, right? Same way, if I have a function f, which is the ratio of two polynomials, then we call f of x to be improper, right? We call f of x improper if the degree of the numerator is bigger than the degree of the denominator, greater than or equal to. And we call the rational function f of x proper if the degree of the numerator is less than the degree of the denominator. Okay? Let's look at a few examples. This fraction here, this fraction is x cubed plus x divided by x minus 1. By the way, what is the degree of a polynomial? Degree of a polynomial is the highest exponent that you see in that polynomial, right? Now, in this fraction, what's the degree of the numerator? The degree of the numerator is 3. The degree of the denominator is 1. So it is an improper fraction. The second one, the degree of the numerator is 3, the degree of the denominator is 3 as well, equal. Still, it's improper. The last one, the degree of the numerator is 3, the degree of the denominator is 4. So it's a what? It's going to be a proper fraction. Everybody understands the difference between a proper and an improper fraction. Yeah, go ahead.
What if they both just
If they have the same degrees, we call them improper still. If the degrees are the same, it's an improper fraction. Yeah, that's my second, that's the second example. Okay. Now, again, going back to your childhood, you remember that if I have the number 3/2, right? Again, rational numbers, these are ratios of integers. I can write 3/2 as what? I can write 3/2 as 1 plus a half, right? So what is 1? 1 is integer plus a half, and half is proper. Okay? So if I have an improper fraction, I can write it as an integer plus a proper fraction, right? Any improper fraction is an integer plus a proper fraction, right? Same thing happens with ratios of polynomials, okay? So if I have a improper rational function, I can always write it as a polynomial plus a proper rational function. Is that clear? I have an improper rational function. I can rewrite that as a polynomial plus a proper rational function. Why is that good? Well, if I know how to integrate proper fractions, I know how to integrate improper as well. Why? Because I can write the improper as a polynomial plus a proper. If I know how to integrate the proper, I know how to integrate the improper because we know how to integrate polynomials. So let me give you an example here. So again, what I'm saying is that I have a rational function f of x, and I can always express it as a polynomial right here, plus, and this guy is proper. This guy is proper, and this guy is possibly improper. So if I have an improper fraction, I can write it as a polynomial plus, so this would be the polynomial, plus a proper fraction. Once again, the reason I did that is that I want to show you how to find integrals of proper fractions. If I know that, I can also handle improper, because I can express improper in terms of proper fractions. Let me give you an example. It's going to make it clear. How do I express, right? How do I express an improper fraction as a polynomial plus a proper? Again, you have to go back to 6th grade or 7th grade probably, where you learn for the first time polynomial division, which I'm pretty sure you have done polynomial division in high school as well, right? So I'm going to remind you how to do polynomial division in a second. If I have a rational function, I have the ratio of two polynomials, right? If I divide the numerator by the denominator by using polynomial division, I have a quotient and I have a remainder, right? And what I have here, the q that I have here, q is the quotient when I divide the numerator by the denominator. So when I divide the numerator by the denominator, I get a quotient, that's q, and I get a remainder r. So that r is right here. That r is right here. Okay? So the q is the quotient, r is the remainder. And then I can express the fraction in this way. Okay? So let's see an example. Let's say I have this rational function which is f of x. F of x is x cubed plus x divided by x minus 1. And what I want to do is I want to express this as this is an improper, right? Improper fraction. I want to express it as a polynomial plus a proper fraction. And let's see how we could do that. Now, when a couple of years back, I taught calculus for pharmacy. Pharmacy students, for them there is a different calculus class, which is basically a baby calculus because it doesn't have trigonometry in it. Okay, so it's a calculus class created only for them. Now, the pharmacy students are smart, but they are smart in a different way. That is, they have a very good memory. They can memorize a lot of things, but their reasoning skills are not as good as the engineers or the other sciences. Okay, and so when I was teaching this course, at some point I was doing polynomial division, and one of the students asked me, "Do you expect us to know this? Do you expect us to know polynomial division?" And I was thinking, is she asking me because she doesn't know it at all, or she just forgot? And my answer was that of course I expect it, because like I said at the beginning, you're supposed to learn it at what age? 6th or 7th grade. And you keep seeing that as you take more and more math classes, right? I'm pretty sure in high school you have seen some polynomial division, at least in pre-calculus, right? It's okay if you forgot this. It's okay it's forgot this. But it's a crime if you don't remember it after I show it. Okay? It's a crime because there is a penalty for it, which is going to be in your exam, right? Okay. Is that enough motivation for you to remember how to do polynomial division? All right, so here's a polynomial division. I am going to divide x cubed plus x by x minus 1. So here is my, what do you call this guy? You call that guy divisor, right? You call that guy divisor. And this first row here, what is that called? Dividend, right? Dividend. It could be called dividend too, but I say dividend because dividend has a different meaning in terms of the business college and so on. So I'm going to say dividend. I think that's probably most of you call that, right? Okay. Now, how do I divide? Well, I have the leading coefficient of the dividend is x cubed, right? The leading coefficient is x cubed. So I have to multiply the divisor with the power of x to match that x cubed. So what do I choose? I choose x squared because when I multiply x squared with the divisor, I do get x cubed. So I'm trying to match the leading coefficient of the dividend. Everybody's clear? So when I multiply, what do I get? I get x cubed minus x squared. Right? All right. So now, what do? When I multiply x squared with x minus 1, I got x cubed minus x squared. What is my next step? We subtract the second row from the previous row. If I subtract now, what do I get? Positive x squared. Yeah, because it is, what you have is the first row minus in parentheses the second row, right? So when you subtract this, you get minus x cubed plus x squared. So when you subtract the second row from the first row, you're going to get x squared, and there is a plus x from the first row. All right. Now my new row has leading power what? X squared. So that's what I have to match. In order to obtain x squared, I have to multiply the divisor with x. So I multiply x and x minus 1, I am going to get x squared minus x. All right, so now I subtract again, and if this time I subtract, I'm going to get x minus x, which is 2x. So I had x cubed canceled out here, x squared canceled out here, subtract, I get 2x. So this is where I am right now. What is my next step? I have to match x, 2x. In order to match 2x, I have to multiply the divisor with the 2. If I multiply the divisor with the 2, I get 2x minus 2, right? Everybody is okay? If I subtract, I get a 2. When do I stop? I stop as soon as the remainder has degree less than the divisor, right? I stop as soon as the remainder has degree less than the divisor. In this case, the divisor has degree 1, so that's why we stop at 2, because it's a polynomial of degree 0. So now, what is the remainder? So this is my remainder r. This whole thing here is my quotient q. Okay? So I can write my, remember, this was my f. That's my rational function. And that rational function is the same as the quotient plus this is the remainder divided by the divisor, right? Everybody's okay? A improper rational function, you do polynomial division, you get a quotient, you get a remainder, and then you set the improper fraction as the quotient plus the remainder divided by the divisor. Everybody's okay? Now notice that if I want to integrate this improper rational function, all I have to do is integrate the polynomial, and I have to integrate this improper fraction, right? Everybody's okay? Now, everybody knows how to integrate polynomials, right? And do we know how to integrate the improper in this case? The proper in this case? Yes, the integral of 1 over x minus 1, right? What is that? That's log of x minus 1, right? So that's why we need to do this in order to integrate this improper rational function. Of course, in most examples, the proper fraction that you obtain is not as nice as this one. Yeah.
So this is just kind of like all the way back. So why is it called proper and improper?
Okay, if I have a fraction,
right.
It's called proper when the degree of the numerator is smaller than the degree of the denominator.
But is that just because, like, is that just...
That's just because...
Okay, that's kind of simple.
That's just a definition.
Okay.
We are naming, we are sort of separating the fractions where the numerators have degree bigger, and from the fractions where the degree of the numerators are smaller. So we are giving them names because...
and we just... Yeah. Oh, that's just because we wouldn't know otherwise how to integrate that.
We don't know how to integrate improper,
right,
unless we write it in terms of proper.
Okay.
Yeah. So we are just giving them names, okay? All right, so here's a little bit of review of polynomials. What is a linear polynomial? If I have a polynomial ax plus b, right? That's a linear polynomial because the degree is 1 and the graph of that is what? The graph of that is a line, right? And then I have a polynomial of degree 2 right here. A, B, C are constants here. A polynomial of degree 2 is called a quadratic. And what's the graph of a quadratic? Yeah, it's a parabola. Exactly, it's a U-shaped. It could be upside down as well, depending on what A is, but in general that's a U-shaped or it's a parabola. Now, it might be a little bit confusing at this point, but if I have a quadratic polynomial, right, I can set it to equal to 0 and get the quadratic equation right here. Again, I said the graph of the quadratic is a parabola, right? If you solve this quadratic equation, what do you get? If you solve the quadratic equation, what do you get? Well, you get the x-intercepts of the graph, right? That is, suppose my parabola looks like this. Suppose my parabola looks like this. So when you solve the quadratic equation, you get these two numbers, right? Okay. However, if the parabola looks like, let's say, looks like this, then it doesn't have any x-intercept, right? In that case, the quadratic equation will have no real solution, right? And in terms of the quadratic formula, what does it mean? When do you not have a solution? Exactly, when b squared minus 4ac is negative, right? When this quantity inside the root is negative, you don't have a solution for the quadratic equation. So we have to be able to separate quadratic polynomials into two. We have to group the quadratic polynomials into two groups. Some of the quadratic polynomials, they have x-intercepts, and some of them don't. The ones that don't have x-intercepts are called irreducible quadratic polynomials. Irreducible. Now the ones that have x-intercepts are called reducible. What is the difference between irreducible and reducible? When you have a quadratic polynomial that has x-intercepts, that is, the quadratic equation has solutions, then you can factor out the quadratic into linear factors. But if the quadratic equation does not have any solution, then you cannot factor it out any further. You cannot factor out the quadratic into linear factors. Am I making sense? So that's important. And so once again, our definition of irreducible is that if I have a quadratic polynomial, I call that irreducible if the corresponding quadratic equation has no solution. When you have irreducible quadratic, it cannot be factored any further. Here's the fact from pre-calculus. Every polynomial of whatever degree, every polynomial with real coefficients can be factored into linear and or quadratic, irreducible quadratic factors. Am I making sense? If I have any polynomial, I can completely factor it out into linear and or irreducible quadratic factors. Okay? Did my statement make sense? Let's look at a few examples of that. Here I have the quadratic polynomial, which is 2x cubed plus 3x squared minus 2x. How do I factor it out? Well, I know that every term has an x, so factor out the common x. So that's what I did here. If I factor that out, I am left with what? X squared plus, it should be 2x squared. 2x squared plus 3x minus 2. Now, 2x squared plus 3x minus 2, is that a reducible or irreducible? Well, you can see from what I have there, it's reducible. But let's just check. Maybe before you do the factorization, you can check whether 2x squared plus 3x minus 2. I ask, is it irreducible? Well, all I do is that I look at the equation, quadratic equation, and apply the quadratic formula to see if I have a solution. By the quadratic formula, this is what? Negative 3 plus or minus the root of 3 squared minus 4 minus 2 and a times 2 and a times minus 2, right? Divided by 2 times 2, right? You guys agree with that? By the quadratic formula, I get this. Now, inside this square root, do I have positive or negative? Positive, because I have a negative, this negative 2 right here, negative 4, that's going to give me a positive, right? So I know that I have a solution. Well, since I have a solution, I know it's reducible. Since I know it's reducible, it better work out that I can factor it out. So if you factor out this quadratic, you get 2x minus 1 multiplied by x plus 2. 2x minus 1 times x plus 2, that's going to be the factorization of that quadratic. How many of you remember how to do that? Everybody remembers to do that. If you don't, in a bit I'll show you what to do to factor that out. Now next, let's say now I have the quadratic x cubed plus 4x. How do I factor it out? Once again, x is the common factor, so let's take that out. And once I take out x, I get x squared plus 4, right? I ask myself, is this irreducible or reducible? Can I factor it out? Well, if I look at the equation x squared plus 4, do I have to apply the quadratic to know if there is a solution? Obviously there is no solution. Why? Because the left hand side, no matter what x is at least 4, right? You guys realize that? Because it's x squared. So no matter what x is, x squared is always positive. So the left hand side is always at least 4, but the right hand side is 0. So there is no solution. So this guy has no solution. So because it doesn't have a solution, I know it's an irreducible quadratic, so I should not even try to factor it out. So this is the complete factorization of that number, that polynomial. The last example. This quadratic, this fourth power, right? How do I factor it out? Whoops. How do I factor this guy? It's actually FOIL because x squared, sorry, actually 4, oops, sorry. What I'm going to do is rewrite this polynomial as x squared, right? Plus 4 times x squared plus a 3. Notice that x squared plus 4x squared plus 3, that's just if I replace x squared by y, I get what? Y squared plus 4y plus a 3, right? And everybody knows how to factor that out. What do you get? You get y plus a 1 times y plus 3, right? And then I replace y by x squared again. So that's how I'm getting this. You guys are okay with that? Everybody sees that? Okay, I am going to erase. I'll keep it for now, I guess. Well, let me just erase what I wrote there, because I don't want to have too many things there. Alright, maybe I'll just use the eraser. Do I have an eraser? Okay, so So everybody knows that every polynomial can be factored into linear and irreducible quadratic. Yeah.
For your last example, you
Yeah.
had x squared plus 1. X squared plus 1 is linear.
X squared plus 1 is quadratic because
Right.
what's the degree? The degree is 3.
Right.
It's irreducible because if I look at x squared plus 1 equals to 0, it doesn't have a solution.
Okay.
So you're right. The x squared plus 1, it has to be quadratic. Okay, so again, our goal is that we want to integrate rational functions. We know that if we know how to integrate proper fractions, we can also integrate improper, because improper is a polynomial plus a proper. So all I need to do is figure out techniques for integrating proper functions, proper fractions, right? This statement in red is the fact that you have to remember. What it says is the key to integrate proper fractions. What it says is that if I have a proper rational function, I can express that proper rational function as a sum of fractions. I can express a proper fraction as a sum of fractions. Now, what type of fractions? Well, each summand either looks like this or this, where in the second case the quadratic is an irreducible quadratic. Is that making sense? Every proper fraction, I can express it as a sum where each summand either looks like number 1 or it looks like number 2. In number 1, I have a linear factor to the power something in the denominator, and a is a constant. Number 2, I have a linear polynomial in the numerator, and in the denominator I have an irreducible quadratic to some exponent k. Okay? So each summand has one of the two forms. So again, proper fraction, I can express it as a sum where each summand looks like 1 or 2. Well, some of the summands, yeah, it should be and or. So some of them should look like this, some of them look like this. Okay. Now, why is this good information? Why, if we are able to do that, how is it good for integrals? Well, how would you integrate something like this? Do we know how to integrate something like that? For example, what if I have 2 divided by, let's say, x plus 1 to the 3? Do I know how to integrate that? What do I have to do? Use substitution, right? By taking u to be x plus 1. How about something like 2x plus 2 divided by x squared plus 2x. Do I know how to integrate that? What do I do in this case? Still, u substitution works because the derivative of the denominator is in the numerator, right? However, the second guy is not always good looking, okay? It is sometimes bad looking in the sense that sometimes the quadratic that you have in the denominator, the derivative of that is not in the numerator. In that case, it's not a simple substitution. In that case, you have to do other things. And I'll show you what other things you could apply. Okay? All right, so, well, some other things would be things like inverse tangent, inverse sine functions, and so on. So we'll see that later. But everybody is clear on one thing, yeah?
What's the letter outside the parentheses where the number is? Is that correct?
This is K. Both of them are K's, yeah. Okay. He's making fun of my handwriting. Okay, so this is K. Sometimes it looks like a kappa when I write it, okay? All right, so everybody can remember the statement in red. The statement in red, every proper fraction can be written as a sum where each summand is of the form 1 or 2. Okay? Well, that's well and good. But the question is, how would you do it? How would you express? So in my handout to you, I gave you a guideline, and this is the guideline. Oh, by the way, when I express a proper fraction as a sum, where each summand is either of the form 1 or the form 2, then that expression is called partial fraction decomposition of the proper fraction. Can you remember that? So when I express the proper fraction as a sum, where each summand looks like 1 or 2, that's called partial fraction decomposition, okay, of that fraction. The question is, how do we find the decomposition of a given rational function? And that's where you need to follow these 4 guidelines that I have here. It turns out the decomposition depends on the denominator. How depends on the factorization of the denominator. Okay? It depends on the factorization of the denominator. So here's the first guideline. Suppose that so remember, I have a proper fraction, I have a numerator and the denominator. Let's say in the denominator you have a factor, linear factor, ax plus b. You have a linear factor. So basically every factor of the denominator gives you a term on the right. Every factor of the denominator gives you a term in the decomposition. Question is, what term? So if I have a linear suppose that I have a linear factor ax plus b. Linear factor in the denominator ax plus b with exponent 1. Okay? For that factor, I will have only one term in the decomposition. If I have a linear factor with exponent 1 in the denominator, that's going to give me one term in the decomposition. What is that term? That term is like this. For some constant a, you'll get a term like that. I'm going to show you how to find a's later. Right now the point is how the decomposition look like. And if I have a linear factor ax plus b in the denominator, for that linear factor, the decomposition term is a constant a divided by that factor ax plus b. However, sometimes the denominator, one of the factors in the denominator is a linear factor, but it has an exponent 2 or 3. right? That is, let's say the denominator, let's say you have x cubed plus 1 divided by x plus 1 to the 3 times x squared plus 1, right? So you have a linear factor here, but that linear factor occurs 3 times. Okay? So when you have a linear factor with an exponent bigger than 1, then what do? Well, suppose that I have a linear factor, but the exponent on the linear factor is k. Then I am going to get k terms in my decomposition. And those k terms are right here. If I have a linear factor with k power, then I am going to get a constant over ax plus b, a constant over ax plus b squared, dot dot dot, up to a constant over ax plus b to the k. Okay? And again, I'm going to show you some examples of how that happens. Everybody is clear on 1 and 2? Three is, what if you have a quadratic factor, right? So suppose that the denominator has a quadratic factor. Then, in the decomposition, we are going to get a term like this, where the denominator is the quadratic factor, but the numerator cannot be just a constant. It has to be a linear factor. So you have a linear function divided by the quadratic factor. So if I have a quadratic factor in the denominator, in the decomposition, I get a term that looks like this. Okay? Everybody is okay with that? What if you have? What if that's like a bad dream if you have a power on the quadratic? Okay, so if you have a power on the quadratic, so suppose you have a factor in the denominator which is a quadratic to the exponent k. Well, then you have k terms in the decomposition like this. Yeah.
Are b on top of the middle line and c on top of the line the same?
Well, the c's are the c1, c2, ck's. They are different.
But
Yeah.
okay.
Which c are you speaking about? Oh, you're talking about here?
Number 3.
Yeah, I should actually, thank you for showing me that. It should be a different c, okay?
So
This-
both b's and c's are different on top of that.
Okay, what I meant here is that I have capital B and capital C versus
Okay.
lowercase abc. Yeah, these are different. Let me put a prime here to make sure those are different. Okay. Now, lowercase abc's, those are fixed because those are in the denominator, and capital B, capital C are the things that you have to find so that the composition works. And I'm going to show you that in a bit. Now, let's just, how many minutes do I have? 3 minutes? Well, it'll be hard to finish this in 3 minutes, but I'll try. Okay, suppose that I have this function. And if you think this is a really bad, long example, I'm actually being nice with this example, okay? And you can imagine that things could be a lot worse if I have a lot worse denominator, okay? So here's here, what is this a proper fraction? You have to make sure you have a proper fraction before you follow the guideline. Okay, so it is proper. The first step, factor out the denominator. So this guy is the denominator, and actually we have seen this denominator in my examples before. Let me skip the steps here how to factor it out. I'm going to give you more examples next time. So let's go directly to the factorization. If I factor out the denominator, I get x times x plus 2 times 2x minus 1. Everybody's okay with that? All right. So my function that I started with, this rational function, becomes this because I factored out the denominator. Okay, now I am going to write down the partial fraction decomposition of this fraction. So this is the fraction I have. I want to write down the partial fraction decomposition. Now I have the factor x. The factor x is a linear factor, right? The exponent on that is just 1. So for that factor, I am going to get one term in the decomposition. What is that term? That term is a constant a divided by the factor x. Everybody's okay? Now I look at the second factor. The second factor is x plus 2. In my decomposition, I am going to get a term where the denominator is x plus 2, the numerator is a constant b. Okay? And for the third factor, 2x minus 1, I am going to get a fraction in the decomposition where the fraction is a constant over 2x minus 1. Everybody's okay? My first step is that I have my proper rational function right here. I am going to write down what is the partial fraction decomposition. So far, I only wrote down how the partial fraction decomposition looks like because I haven't found out what is A, B, and C, right? So for what A, B, and C will this equation hold? I have to find that as well. What I'm saying so far is that there is a value of A, there is a value of B and C for which this equation will hold. That's what we have said so far. But I have to find those values as well. Okay? How do I find those values? I'm going to skip that part today as well because I want to get to the last line. I'm going to show you how to find A, B, C. It's a little bit more, it's a little bit tedious. So I'm going to go and I'm going to tell you what are A, B, and C. A turns out to be half. A turns out to be a half. B turns out to be a tenth. And C turns out to be 1/5. Again, I'm going to show you later how to find those values. I haven't showed you that. Now, so why is this decomposition good? Well, if I integrate the proper fraction, if I want to integrate the proper fraction, I can integrate what? I can integrate the decomposition. So all I have to do is integrate 1 over x. I have to integrate 1 over x plus 2. I have to integrate 1 over 2x minus 1. Do I know how to do those? Yes, because I can apply the log. So the integral of 1 over x is log of absolute value of x, integral of 1 over x plus 2, integral of 1 over 2x minus 1. Okay? So that's why so remember, what are the steps? We started the first step, factor out the denominator. Second step, write down the decomposition form. Third step, solve for ABC. Fourth step, integrate. Okay? 4 steps. Alright? Now, in my handout, I gave you problems, so make sure you try to do those problems, okay? Next time, I am going to work on the board. I'm going to show you examples after examples, okay? Yeah.
There's a slide that I didn't get all the information written down for, and I wanted to just finish it.
The slides that I gave you before the break has everything that I said, but still, if you want, you can take this. This has everything there. Yeah.
Are you at the same place in your 10 o'clock section?
Say it again?
Are you at the same spot?
Oh, yeah.
I have a job interview on Wednesday. It's going to take me out of
You can
class.
come to the morning section.
Okay.
On Wednesday, you mean?
Yeah, on Wednesday.
That's fine.
Okay. Thank you very much.
Is that an internship?
Yeah. I have practice.
Quiz.
Well, I have practice. Can I take it tomorrow sometime?
Tomorrow is not good. You have practice on Wednesday as well?
Yes, right after that.
Do you have another time like
Recommend before class on Thursday?
before?
Because I have
Right before class, at least come 20 minutes before the 20 minutes.
I think very good.
You are,
I can take it down, unless you prefer I take it Thursday.
no, just to give me 1 second.
Okay.
Do you want them
You're
back?
done?
Or?
Yeah. You can keep them.
Oh, cool.
You are here for the quiz too?
Just laying up here.
Oh, okay. Okay.
Says the person who sleeps.
There's nothing bad with that.
Slow and steady is good. Okay, I better not lose what I was trying to do there. Okay. Okay. No, everything's okay.